Welcome everyone. Now we will look at Fourier transform properties. So to remind us once again, the synthesis equation is xt equals 1 over 2 pi integral from minus infinity to infinity x j omega e to the power of j omega t d omega. Remember the integral is in omega and here the sign is positive. Also we have the analysis equation. X j omega is the Fourier transform integral from minus infinity to infinity xt e to the power of minus j omega t dt. So when we have to compute the Fourier transform, we use equation number 2. Given the Fourier transform, when we want to reconstruct the signal or to do the inverse Fourier transform, we use equation number 1. So we represent this relationship in a compact fashion as xt having the Fourier transform capital X j omega. First relationship is linearity. If xt has the Fourier transform x j omega and yt has the Fourier transform y j omega, then axt plus byt, a linear combination of the two signals, has the Fourier transform ax j omega plus by j omega. So it is the same linear combination of Fourier transforms. Then when we think about the time shifting, assume that xt has the Fourier transform x j omega, then we want to find the Fourier transform of the time delayed signal x t minus t naught. So here t naught is a constant. It turns out it is equal to e to the power of minus j omega t naught x j omega. So the same Fourier transform here multiplied by e to the power of minus j omega t naught. Okay, let's go for a small proof of that. So let's write the synthesis equation xt equals 1 over 2 pi integral minus infinity to infinity x j omega e to the power of j omega t d omega. So let's just substitute t equals t minus t naught over here. Then we realize that we can write that exponential as a multiplication e to the power of minus j omega t naught x j omega times e to the power of j omega t. So when you realize this, this has the form of this. So then we realize we have essentially done is writing the synthesis equation of this signal e to the power of minus j omega t naught times x j omega, that Fourier transform. So therefore, it must be true that the Fourier transform is xt minus t omega is this one. Okay, so if we examine this, the magnitude of the Fourier transform is not altered. So you can see e to the power of minus j omega t naught has a magnitude 1. So the magnitude has not been altered, but the time shift introduces a phase shift minus omega t naught, which is linear, which is a linear function of omega. Okay, now we can use that property and the linearity to obtain Fourier transform of a signal like this. So when we look at this signal, we realize that we can express that in this fashion. That means we decompose that to x1t, which has magnitude 1 and goes from half to half, and x2t, magnitude 1, goes from minus 1.5 to 1.5. And if we have defined x1t and x2t, this xt can be written using x1t and x2t. So of course we have to shift this origin to 2.5, which is what we have done here, t minus 2.5, and we have to multiply the first signal by half so that we get xt. Also we know that for a rectangular pulse like this, actually the pulse in time domain has this form from minus t1 to t1 it is 1, otherwise it is 0. So if you take this rectangular pulse, its Fourier transform xj omega is 2 sine omega t1 divided by omega, which we did some time ago. So we can use this Fourier transform to express Fourier transforms of this signal and that signal. So it turns out that x1 j omega is equal to 2 sine omega divided by 2 over omega. x2t is 2 sine 3 omega divided by 2 over omega. So here you can see t1 in this case is half. So here it's 3 by 2. So you can see how we have obtained them by writing t1 over there. Okay, and these two signals are there, but then you have to apply the time delay of 2.5 seconds. So e to the power of minus j5 omega divided by 2. So this completes the example. Alright, now let's look at conjugation and conjugate symmetry. Now in this case also we are given xt and its Fourier transform is jxj omega, and we want to find out the Fourier transform of the conjugated signal x star t. So we know that if we have some complex number like 4 plus j5, its complex conjugate is 4 minus j5. So it turns out that the Fourier transform of the complex conjugate is x star minus j omega. So in addition to conjugating x, we have to reverse the frequency axis. Okay, so let's try to obtain this. So Fourier transform of x star j omega is you take the Fourier transform of x j omega, so this one is x j omega, and get the complex conjugate of that. So when you get the complex conjugate, you have to conjugate this as well as this. So there you get the sign has changed and this has become the conjugate. So now we replace omega by minus omega, and then we realize that this is the analysis equation of x star t, which is actually the complex conjugate of xt. So there you go, the answer. Okay, now let's consider this situation. If xt is real, what is the situation if xt is real? So there is no imaginary part in that signal. So therefore xt is equal to x star t. So j omega should have conjugate symmetry because this and this must be equal in that case. Xj omega and x star minus j omega must be equal. So therefore it has conjugate symmetry. So we must remember this. Okay, using conjugate symmetry, to comment about the summary symmetry of the Fourier transform of a signal xt, if xt is real and even, and xt is real and odd. Okay, so now let's express x j omega in rectangular form as the real part and the imaginary part of that. So what we are doing is if you take some z equals 4 5 plus j5, so real part of z is actually 4, imaginary part of z is 5, so we must write z as 4 plus j5. That means real part of z plus j times imaginary part of z. So it's very just to show you what this means. Then if xt is real, then xt we know is equal to x star t if xt is real. Then real part of xj omega must be equal to real part of x minus j omega. So we have to get the relationship from before. So that means we know that x minus j omega is x star j omega. When xt is real, we have conjugate symmetry in the Fourier transform. As a result, if we take the real part of xj omega, then we don't have to consider the complex conjugate of that real part. So it is equal to the real part of x minus j omega, and the imaginary part is conjugated. You can see the minus sign here. Imaginary part of x j omega is equal to minus imaginary part of x minus j omega. That is, the real part of the Fourier transform is an even function of frequency, and the imaginary part of the Fourier transform is an odd function of frequency. So you can see, because of this minus sign, it's an odd function. Okay, if we express x j omega, the Fourier transform, in a polar form, magnitude of x j omega times e to the power of angle of j omega, we see that x j omega is an even function of the frequency, and the angle x j omega is an odd function of the frequency. So the angle we get by taking a tan 2 of this divided by this. So you can see it is an odd function. The imaginary part, of course, the magnitude, of course, is real because of when you consider this square them and get the square root. This is for a real signal, only for this one. Okay, if xt is both real and even, then what is the situation? Then x j omega will also be real and even. So let's have a brief proof of that. Consider x minus j omega real and even. So for real signal xt, we have x j omega star is equal to x minus j omega. So let's write that in the same form as we did here. X minus j omega is x star j omega. Is only exterior. For exterior, we have this relationship. So x minus j omega. So substituting tau equals minus t. So we put minus tau here, tau there. Since xt is real and even, x minus tau is equal to x tau because it is an even signal. So we can just write x tau here. This turns out to be the Fourier transform of x, which we represent as xj omega. So x minus j omega is xj omega. In a similar manner, it can be shown that if xt is real and odd function of time, so that xt is equal to minus x minus t, then xj omega is purely imaginary and odd. Okay. So now let's consider the Fourier transform of odd and even parts. A real function xt can be expressed as xt equals x even part of t and x odd part of t. So this is the even part, this is the odd part. So we know the formulae for this. So x even part of t is equal to xt plus x minus t divided by 2, and x odd part of xt is equal to xt minus x minus t divided by 2. So we represent et as even part with these characters xt, and the odd part as x odd t, odd part of xt. So express the Fourier transform of x even part of xt and odd part of xt in terms of xj omega. That's the question. Okay, so Fourier transform of xt is equal to the Fourier transform of x even part of xt and the odd part of xt. And from the preceding discussion, Fourier transform of x even part of t is a real function because it is even, and the Fourier transform of x odd part of xt is purely an imaginary function of frequency. Thus, we can conclude that with xt real, so xt has a Fourier transform of xj omega, even part of xt, Fourier transform of the real part of xj omega, and the odd part of xt, so Fourier transform is j times imaginary part of xj omega. So because we know that Fourier transform x even part of t is must be a real function. That's why this must be purely imaginary. Right. Okay, we'll take an example of this. Use the symmetry property of the Fourier transform to evaluate the Fourier transform of xt equals e to the power of minus a absolute value of t y greater than 0. So we have already computed the Fourier transform of xt equals e to the power of minus at. We have done that. So what we want to do is we use this to compute that. We have already found that this is the answer. So I will not go through this now. So let's consider xt now, e to the power of minus a modulus of t, that is equal to e to the power of minus at ut plus e to the power of at u minus t. So y greater than 0, we know that this is e to the power of minus at ut, and I can sketch e to the power of at u minus t as this dotted line. So when you add those two signals, you get this. So now if we multiply by 2 and divide by 2, we realize that this is actually the even part of e to the power of minus at ut, twice the even part of that. So what is the Fourier transform of the even part? It's the real part of the Fourier transform. So since e to the power of minus at ut is real valued, the symmetry property of the Fourier transform leads us, properties of the Fourier transform lead us to conclude that even part of e to the power of minus at ut is actually the real part of the Fourier transform of that signal. So therefore, xj omega Fourier transform of this is 2 times real part of 1 over a plus j omega. That turns out to be 2a divided by a squared plus omega squared. So when we actually did this using first principles, we got this answer. So how do we get the real part of this one? So 1 over a plus j omega, we can multiply the numerator with a minus j omega and the denominator with a minus j omega, the complex conjugate. And then here you get a squared plus omega squared. Here you get a minus j omega. So if you take the real part of that, is actually a over a squared plus omega squared. Okay, so you have to get twice of that to get this answer. Okay. Let's look at differentiation and integration properties. So once again, the synthesis equation is xt equals 1 over 2 pi this integral. And if you differentiate both sides with respect to t, you can see e to the power of j omega t is the only term that has time t, and we get j omega in front. So what this means is, now this is actually the synthesis equation for j omega x j omega Fourier transform. With that Fourier transform, we synthesize the signal, and we know that that signal is dxt by dt. Given the Fourier transform, how do we find the Fourier transform of the derivative of the signal? We just multiply it by j omega. The integration property running integral minus infinity to t x tau d tau has a Fourier transform 1 over j omega x j omega plus this constant pi x0 delta omega. So we must not forget this part. Alright, let's do an example. Determine the Fourier transform of the unit step xt equals ut, making use of the knowledge of that gt equals delta t has a Fourier transform 1. So let's designate that as gt. Its Fourier transform of gj omega. Its Fourier transform is 1. We know that for the unit impulse, the Fourier transform is 1. So we know that if we integrate g tau, actually g tau is delta t, integrate delta t, we know that you get ut. So therefore, to get the Fourier transform, we have to write 1 over j omega g omega pi g0 delta 0. So since j omega is 1, we can write in this fashion, which is the Fourier transform of the unit step. And observe that we can apply the differentiation property to recover the transform of the impulse. So delta t is actually dut by dt. So that's Fourier transform is j omega times 1 over j omega pi delta omega. In this case, you can see that since we are multiplying with omega, we can use omega delta omega is equal to 0 property. So therefore we recover 1 out of this. Okay, let's take one more example. Determine the Fourier transform of the signal xt shown below. So you can see this xt is actually the integral of the xt is actually the if you differentiate xt, we get gt, but remember we get these two impulses also, because here we are transiting from 0 to negative 1, and here from 1 to 0. So because of that, we have these two impulses of height -1. So therefore j omega is equal to 2 sine omega omega minus e to the power of j omega minus e to the power of minus j omega, and these two are for these two impulses, and this is for the rectangular parts. And now xj omega is equal to 1 over j omega gj omega plus pi g0 delta omega, using the integration property. As g0 is equal to 0, we have xj omega is equal to 2 sine omega divided by j omega squared and 2 cos omega divided by j omega. So we can also realize that xj omega is purely imaginary and odd, because this is an odd symmetric signal. So how do we get this one? If you put sine omega omega, when omega is equal to 0 is 2, and here we put zeros, and we get when you put omega equals 0 and omega equals 0, you get -2, and that cancels off and you get 0. Okay. Then time and frequency scaling. If xt has a Fourier transform xj omega, xat has a Fourier transform 1 over modulus of a xj omega divided by a, where a is a real constant. So if we let a equals -1, x minus t has a Fourier transform x minus j omega. The scaling property is another example of inverse relationship between time and frequency. What this means is if a is equal to 2, that means we compress the time domain signal in the time axis. That means in the frequency domain, spectrum expands in omega axis. That's the inverse relationship. Okay, then duality, another important property, because the similarity between the synthesis equation and the analysis equation. So what is that similarities? And both are integrals. And this is a continuous signal, and this is also a continuous signal. Because of this, in spite of this constant, they look similar. For any transform pair, there is a dual pair with the time and frequency variables interchanged. So we determine the Fourier transform of the square pulse as x1 equals 1 when t is modulus of t is less than t1, and when modulus of t is less than greater than t1, it's 0. So this square pulse, so that has a Fourier transform 2 sine omega t1 over omega, which we have done before. So I have plotted that here. Now see, if we have a time domain signal that looks like the sync pulse, so we also determined that for a time domain signal that is similar to the shape x1 j omega, we determined that. So if you have a time domain signal sine wt divided by pi t, this signal, its Fourier transform turns out to be this square pulse of with minus w to w. So therefore, Fourier transform of x1t is x1 j omega, and if we construct a time domain signal that looks like this x1 j omega, but now the signal is in time domain, w over pi, there is some scaling factor and so on, its Fourier transform turns out to be like this. This is the duality. So using duality, we can derive theorems. Now, before that, we can do an example. Use the duality property to find the Fourier transform of capital G j omega of the signal, this signal. To find the Fourier transform of this signal, we use this knowledge. Consider the signal xt whose Fourier transform is x j omega equals 1 over 2 1 plus omega squared. So instead of t, we put omega squared, and consider a Fourier transform that looks like this time domain signal. So we know from our previous experience that xt equals e to the power of minus modulus of t's Fourier transform is 2 over 1 plus omega squared. So actually, if you remember, we got for xt equals e to the power of minus at modulus of t, we got the Fourier transform 2a divided by a squared plus omega squared. So using that, we put set t a equals 1 to get this. Alright, the synthesis equation for this Fourier transform pair is this. So we can reconstruct the time domain signal e to the power of minus modulus of t using the synthesis equation 1 over 2 by integral minus infinity to infinity the Fourier transform times e to the power of j omega t d omega. So we use the Fourier transform x j omega there. So this is x j omega. Okay, let's proceed. Multiplying this equation by 2 pi and replacing t by minus t, we obtain 2 pi e to the power of minus modulus of t, it doesn't change, in integral minus infinity to infinity 2 over 1 plus omega squared e to the power of minus j omega t d omega. Now, interchanging the names of variables t and omega, 2 pi e to the power of minus modulus of omega is equal to minus infinity to infinity 2 over 1 plus t squared e to the power of minus j omega t dt. So what is this equation? The right hand side of the expression is the Fourier transform analysis equation for this time domain signal. That means if we take this time domain signal, we must get this Fourier transform. Okay. So you can see, by using the knowledge of a Fourier transform, we were able to obtain the Fourier transform of a time domain signal that looked like the Fourier transform of a particular time domain signal. So we knew the Fourier transform of e to the power of a equals 1 t, this signal, Fourier transform. So using that knowledge, we were able to obtain the Fourier transform of a similar looking time domain signal that was similar looking to the Fourier transform 2a divided by a squared omega squared. You see, this is a function of omega and this is a function of t. That looks like that, and this looks like this. So more properties using the duality. So we can, if we differentiate the Fourier transform, its time domain signal is minus jt xt. So if you take the frequency shift x j omega minus omega naught, that's time domain, corresponding time domain signal would be e to the power of j omega naught t x t. Also the running integral in the frequency domain, that would have 1 over minus 1 over jt xt pi x0 delta t. Okay. Then we have the Parseval relation, once again similar to the Fourier series. Integral minus infinity to infinity x modulus of x squared dt is equal to 1 over 2 pi Fourier transform x g omega squared d omega. The relationship was very similar in the frequency in Fourier series. So in the Fourier, as far as Fourier series was concerned, minus infinity to infinity should be replaced with the integral over one period, right? 1 over t integral over one period xt squared dt turned out to be summation modulus of ak squared. So you can see the similar relationship here. Okay, now we can look at the convolution property. If we have a system and input xt to that, our system has impulse response ht, and think that it outputs yt, we obtain yt as the convolution between ht and xt. Assume that this is a linear time invariant system. If you take the Fourier transform of yt, that is yj omega, turns out that it's a product of the Fourier transforms of the impulse response ht and the Fourier transform of xt. This is a very important relationship and we must all remember this. This equation is of major importance in signals and systems. This says that the Fourier transform maps the convolution of two integrals into the product of the Fourier transforms. So pictorially, it's this. An example, an LTI system has the impulse response ht equals delta t minus t naught. If the Fourier transform of the input signal xt is xj omega, what is the Fourier transform of the output? So let's consider this. Okay, so ht has been given delta t minus t naught. And now if we get the Fourier transform of that, we know that hj omega is equal to e to the power of minus j omega t naught. Actually, delta t's Fourier transform is 1, and to account for this time delay, we multiply that with e to the power of j omega t naught. So yj omega, we know from the previous theory that x must be xj omega times xj omega. So we have e to the power of j omega t naught xj omega in this case. So what is the frequency response of the differentiator? So yt is equal to dxt by dt, that's the differentiator. From the differentiation property, yj omega is equal to j omega x j omega. We know this theorem, the differentiation property. So therefore, this must be the multiplication of h j omega and x j omega. So therefore, our h j omega must be just j omega. So one more example, consider the response of an LTI system with impulse response ht equals e to the power of minus at ut, a greater than 0, and to the input signal xt equals e to the power of minus bt ut, b greater than 0. So rather than computing the convolution in time domain yt equals xt convolved with ht directly, we can find yt by transforming the problem into the frequency domain. So therefore, first of all, for xt e to the power of minus at ut, so xt is e to the power of minus bt ut, the Fourier transform is 1 over b plus j omega. For h j omega, because our ht is e to the power of minus at ut, the Fourier transform is 1 over a plus j omega. So yj omega is the product between these two, and you get 1 over a plus j omega times b plus j omega. To determine the output yt, we wish to obtain the inverse Fourier transform of yj omega. This is most simply done by expanding yj omega in the partial fraction expansion. So we have to write the partial fraction expansion in this form. Yj omega is equal to a over a plus j omega plus b over b plus j omega. We must find the capital A and capital B constants. So if b is not equal to a, then a turns out to be 1 over b minus a, and it is also minus b. So this is the partial fraction expansion. So take some time on your own to do the partial fraction expansion. And then by inspection, we know what these signals look like in time domain if their Fourier transforms are 1 over a plus j omega and so on. So this is it turns out to be e to the power of minus at ut. This is e to the power of minus bt ut. But if a is equal to b, we have this form. For that, we have to use the Fourier transform tables. Recognizing this as 1 over a plus j omega squared, actually that is j times d by t omega, 1 over a plus j omega, we can use the dual of differentiation property, e to the power minus at ut has a Fourier transform 1 over a plus j omega, then t e to the power minus at ut has the Fourier transform j derivative of 1 over a plus j omega. So that is 1 over a plus j omega squared. So it turns out that yt is equal to t e to the power of minus at ut. So to know this relationship, we can turn to the tables. We can use the basic Fourier transform pairs table and find out that when you have t e to the power of minus at ut, its Fourier transform is 1 over a plus j omega squared. All the other Fourier transforms are also listed here. So you can refer to this table. In an exam situation, this table must be given. Also, on the other hand, we can use the properties of the Fourier transform. That means, for example, this is the property that was used in the example. Okay, then the multiplication property. The convolution property states that convolution in time domain corresponds to the multiplication in frequency domain. Because of the duality between time and frequency domains, we would expect a dual property also to hold. That is, multiplication in the time domain corresponds to convolution in the frequency domain. Specifically, if we have two time domain signals multiplied st and pt, giving rt, its Fourier transform rj omega is actually 1 over 2 pi, see the constant, sj omega convolved with pj omega. Sj omega is a Fourier transform of xt, pj omega is the Fourier transform of pt, and this is the convolution in the frequency domain. Multiplication of one signal by another can be thought of as using one signal to scale or modulate the amplitude of the other. So this is like multiplying pt by st. Consequently, the multiplication of two signals is often referred to as amplitude modulation. For this reason, this equation is sometimes referred to as a modulation property. So we can pictorially see this. Let's say st be a signal whose spectrum is depicted in the figure below. So let's consider j omega is like this from minus omega 1 to omega 1. Also consider the signal pt equals cos omega naught t, and now we want to show the spectrum of rt equals st times pt. We know that cosine signals Fourier transform is pi and pi at minus omega naught and omega 1, and we have to do the convolution between sj omega and pj omega. So then you know when you have an impulse, that signal actually replicates over there. So minus omega naught minus omega 1 to minus omega naught plus omega 1, this signal, and this also happens also because of that 1 over 2 pi constant, and here also it's replicated. Okay, so what we looked at today was on properties of the Fourier transform. So rather than using first principles to compute the Fourier transform, we can use the Fourier transform properties to compute other Fourier transforms. So also we saw the important property, the duality property, the multiplication property, and the convolution property. Thank you.